Hey everyone, ready to go deep. Today we're taking a look at something pretty wild. Using black holes for energy, propulsion, even messing with time.
Yeah, it sounds like something straight out of a movie, right?
Straight out of science fiction.
Yeah. But the crazy thing is, there's actual research on this stuff.
Oh, really?
Yeah, the two papers we're looking at, black holes, quantum information, energy and propulsion, and remote black hole manipulation via quantum entanglement. They basically say, we could actually do this.
Okay, so you're telling me black holes aren't just giant space vacuum cleaners.
That's the usual picture, yeah.
Right.
But these papers, they say, no, black holes are like the most powerful energy sources in the universe. We just got to figure out how to use them.
Okay, color me intrigued. But how? How do we even start to think about getting energy from a black hole?
Well, the key is information.
Information.
Yeah.
Like what I'm getting from this deep dive.
Well, sort of,
Yeah.
but more like the fundamental stuff of the universe. See, these papers, they say information isn't just data, it's tied to energy.
Oh, okay, I think I'm following. So like more information equals more energy.
Exactly. You're getting it.
Sure.
Think about the Bekenstein bound. It's this idea that the more information you pack into a space, the more energy it can hold.
So a black hole, being super dense, must be packed with information, which means
Tons of energy.
mind blown. But how do we tap into it?
All right, buckle up, because this is where it gets wild. The papers talk about stuff like the Penrose process and Hawking radiation, things that sound like they're from Star Trek.
Okay, I'm definitely buckled up. Hit me with it.
Let's start with the Penrose process. Imagine a black hole spinning crazy fast, right? Like a top.
Okay, got it.
So around that black hole, there's this zone called the ergosphere. It's basically space itself being dragged along by that spin.
So it's like the black hole's gravity is making space itself swirl around it?
Yeah, and that's swirling, that's energy. And the Penrose process says, hey, we might be able to grab some of that energy as it spins.
Whoa, so we'd be like stealing energy from the black hole's spin without getting sucked in.
Exactly. It's like, skimming a little bit off the top without disturbing the whole thing.
That's wild. And what about this Hawking radiation? How does that fit in?
Hawking radiation is the idea that black holes actually leak a tiny bit of energy. They're not completely black, you know?
Okay, so even black holes can't hold on to everything forever.
Exactly.
Huh.
So these papers, they ask, could we control that leakage? Could we maybe even make it bigger to get more energy out?
Okay, now this is starting to sound a little dangerous. We're talking about manipulating the most powerful objects in the universe. How do we even start to test these ideas without, accidentally creating a black hole in the lab?
Well, that's the cool part. The papers suggest we could actually start experimenting right here on Earth.
Wait, seriously? We can do black hole research from Earth. I need to hear more about this.
One way is to use this thing called quantum entanglement.
Yes, that spooky action at a distance.
Exactly. The idea is to take two entangled particles, those particles that are linked no matter how far apart they are, and send one towards a black hole.
Well, hold on. We're going to shoot a tiny particle into a black hole. What's that going to tell us?
Okay, so here's the thing. We keep the other entangled particle here on Earth, right?
Right.
And because they're entangled, whatever happens to the one near the black hole, we can detect it in the one here on Earth.
So it's like having a sensor that reaches all the way to a black hole.
You got it. We'd be able to feel what's happening to the particle near the black hole, even though it's billions of light years away.
This is incredible. So we're using quantum mechanics to study black holes. That's some next-level science right there.
It's pretty amazing, right?
Totally. But what about the particle that goes into the black hole? Isn't that, a one-way trip?
Well, yes, but the information it carries, that's what we're after.
So even though the particle itself is gone, the information it had, that connection, that somehow stays.
Exactly. And that's how we can learn about what's happening inside the black hole, by looking at the changes in its entangled partner here on Earth.
Okay, my brain is officially fried. We're using quantum entanglement to basically spy on a black hole from billions of light years away.
And that's just the beginning. The papers also talk about manipulating these things called virtual particles, which exist near the event horizon.
Virtual particles. Okay, you're going to have to explain that one.
All right, so imagine these tiny particles popping in and out of existence all the time near the edge of the black hole.
Like they're just appearing and disappearing.
Yeah, like little bursts of energy almost. They're called virtual particles because they don't really stick around.
So how do they even matter if they just pop in and out like that?
Well, the researchers say we might be able to influence them using information. like carefully structured information.
Wait, structured information. How do you structure information?
Think of it like creating waves in a pool. You need to drop something in, create a disturbance to make the waves.
Okay, I can picture that.
So the researchers think that by sending carefully crafted quantum states towards a black hole, we could create a similar disturbance in the virtual particle field.
So instead of dropping a rock in a pool, we're dropping information into the fabric of space-time.
And that could potentially influence which virtual particles become real particles and escape as Hawking radiation, giving us a way to control that energy flow.
Wow, that's a lot to take in.
Yeah.
I think I need a moment to process all of this.
Yeah, it's definitely mind-blowing stuff. We've gone from black holes as cosmic monsters to black holes as potential power sources. But before we get too carried away with the possibilities, the big question is, how do we actually test all of this?
Right. How do we move from theory to reality? How do we make sure we're not just, making all of this up?
Well, that's where the experiments come in, and that's what we're going to dive into next.
Okay, because I am hooked. Let's get into those experiments. I want to know how we can actually test this wild stuff out.
You got it.
All right, let's do it. Okay, so we're talking about testing this black hole stuff here on Earth using quantum entanglement to peek into a black hole from billions of light years away.
Yeah.
That's crazy. But you mentioned other experiments too, Earth-based ones. What else can we do?
Well, one idea is to look at how gravity affects entangled particles right here on Earth, like setting up these things called quantum optics experiments.
Quantum optics experiments. Sounds complicated.
It's not too bad. Basically, we're talking about using lasers and mirrors to make and control entangled photons.
Photons. Those are like particles of light, right?
Yep, exactly. Tiny little bits of light. And we can entangle them, link them together in a special way.
So we're using light to steady gravity.
Yeah. The idea is to create these entangled photons and then mess with the gravity around them, make tiny, tiny differences in the gravitational field.
So we're not creating a black hole in the lab.
No, of course not.
Okay, good.
But we're making a little environment where we can see how gravity affects these entangled photons.
Like a mini black hole simulation.
Kinda, yeah. And then we look for anything strange, anything that doesn't fit with how we think quantum mechanics should work.
So if the photons start doing weird stuff when we tweak the gravity, that could mean
that gravity's messing with their entanglement, which would be huge.
It would support these theories, right? About information and black holes and all that.
Yeah. It wouldn't be proof, but it would be a big step. And the best part is we can do these experiments right now. We've got the technology.
That's so cool. So we're using what we know about quantum mechanics to try and figure out even more about gravity and black holes.
Yeah.
It's like solving one mystery by looking at another mystery.
Exactly. And then there are simulations too.
Oh, yeah. You mentioned those earlier. What's the deal with the simulations?
So with simulations, we can really dive into the specifics, like that idea of manipulating virtual particles near a black hole's event horizon.
Right, those virtual particles that pop in and out of existence.
Yeah, those. We can actually create a virtual black hole in a computer.
Whoa, hold on. A virtual black hole? Are you serious?
Yep. We build this digital black hole, put in all the physics we know, gravity, quantum mechanics, everything.
And then we can, run experiments on it without having to worry about it swallowing the Earth.
Exactly. We can play around with it, see how it behaves.
So how do we use this virtual black hole to study Hawking radiation and information manipulation? I'm still a bit fuzzy on that.
Okay, so remember those virtual particles. In our simulation, we can watch them, see how they act according to the laws of physics. Then we can introduce information into the simulation.
Information, like ones and zeros.
Kind of, but more like specific quantum states, carefully structured. It's like, remember that analogy with the pool?
Dropping something in to make waves.
Yeah. So we can see if this structured information, this quantum drop, if you will, can affect which virtual particles become real and escape as Hawking radiation.
So we're testing if we can control the black hole's energy flow in the simulation. That's brilliant.
It's a way to experiment safely before we even think about messing with a real black hole. And we can run the simulation over and over, tweak things, see what happens.
It's like a giant sandbox for black hole science. I love it. But you mentioned one more thing, observing real black holes. How can we do that when they're so far away?
We already have telescopes and observatories looking at black holes all over the universe.
Right.
The key is to analyze the data with these new theories in mind, to look for anything that suggests these processes are happening naturally.
So we're searching for clues, Like cosmic fingerprints that could back up these theories.
Exactly. We're looking for anything that deviates from what we expect based on our current understanding. It's like being a detective, searching for tiny anomalies that could unlock a huge mystery.
That's so cool. So we have these lab experiments, these simulations, and we're also looking at real black holes for evidence.
Yeah.
It's a huge effort.
Yeah, it's a multi-pronged approach.
Just like we're trying to understand black holes from every angle.
We got to be thorough, right?
Absolutely. But even if we figure all this out, how do we actually use it? What are the practical applications of messing with black holes? It's not like we could just build a black hole power plant, right?
Well, the practical stuff is still a long way off, but that's not the point, really.
What do you mean?
The point is the discovery, the pushing the boundaries of what we know. This research could change everything about how we see the universe, how we understand information, energy, even consciousness itself.
Consciousness. Okay, now we're really going deep. But I'm fascinated.
It's all connected, you know?
So it's not just about building cool gadgets powered by black holes.
It's about understanding the universe at its most fundamental level. And that's pretty awesome, don't you think?
Absolutely. It's about pushing the boundaries of human knowledge and exploring the universe's greatest mysteries. And that's definitely worth diving into.
I couldn't agree more. This is just the beginning of an incredible journey of discovery.
Well, on that note, I think we're ready to tackle the big picture. What does all of this mean for us, for humanity, for our place in the cosmos? What happens when we start messing with forces this powerful? We'll get into all of that after a quick break. All right, we're back, and I'm still reeling from that last segment. Black holes as power sources, virtual particles, simulations. It's a lot, but now I think it's time to take a step back, look at the bigger picture. What does all this research actually mean? Like for humanity, for the universe, where does it all fit?
That's the million-dollar question, isn't it? You know, we've been talking about harnessing black holes, but maybe the real revelation here is in how we see information.
Okay, how so?
Well, these papers suggest that information isn't just like a side effect of stuff happening. It's like a core ingredient of the universe itself, like baked into the very fabric of reality.
Whoa, so you're saying information is more than just data. It's like the blueprint of everything.
Yeah, kind of like that. They're saying that if we can manipulate information at the level of black holes where gravity is the strongest, well, that means information's got to be way more important than we ever thought.
Okay, I can kind of see that. But it's also a bit scary, isn't it? Like we're realizing we might have the keys to the universe's control panel, but we don't know which buttons to press yet.
It's true. There's a lot we don't know. And that's why these experiments are so crucial. It's not just about proving a theory, it's about understanding information at the deepest level. How it connects to energy, gravity, maybe even consciousness.
Consciousness. Now that's a whole other deep dive.
Right. But it's fascinating to think about. What if our thoughts, memories, our sense of self are all just patterns of information? Like, what if we are the information?
Mind blown. It's almost too much to think about. Like the universe just became way more mysterious.
And way more exciting. Think of the possibilities. If we crack the code of information, we could change everything. Energy, space travel, even how we understand our own minds.
It's incredible, but also a little terrifying. We're talking about messing with forces we barely understand. What if we screw it up?
Yeah, that's a real concern. And the researchers know that. They're saying we got to be careful, ethical. We got to respect the power of what we're dealing with.
So it's like walking a tightrope between exploring the unknown and not messing everything up.
Exactly. Like, we're explorers heading into uncharted territory. We're excited, but we got to be cautious, too. We could discover amazing things, but we also got to be ready for the unexpected.
Well, I think that's a perfect way to wrap things up. Today, we dove into the mind-bending world of black holes, quantum entanglement, and the very nature of information. It's a journey that's left me with more questions than answers, but that's okay.
Yeah, sometimes the best discoveries start with asking the right questions.
Exactly. So to everyone listening out there, keep asking those questions, keep exploring, keep wondering. The universe is full of mysteries, and it's up to us to unravel them. And who knows, maybe someday we'll be able to harness the power of black holes, travel to distant stars, and even unlock the secrets of our own minds. Until then, keep looking up and keep diving deep.